Yeah, we can.
Okay. Thank you. So previous session I discussed underfitting and overfitting, and today we will see how can we train a machine learning model to solve a given problem. So we have prepared data. We have divided data into two parts, training and test. And now using training part, we will train machine learning model, right? So here first we will see a linear regression model to solve a regression problem, right? Because we are predicting a house price. So we are predicting a real valued output given some inputs, right? So some inputs are given and we will use these inputs to predict one real valued output. So again, it's a regression problem because we are finding relationship between input and output, right? Yes. So for that, we can there are several models, but first I'm using here linear regression model, right? So linear regression model we can import using scikit-learn.linear model, and here we can use linear regression, right? And then we will fit our data to this model, right? Because we are using linear regression model, so we have to fit the data set that we have prepared, right? So this housing underscore prepared is a variable that contain our data set, training data set, right? Because we have split our data set into two parts, training and test. So this training data set, this variable contain, right? And this housing label is the output label because we are doing a supervised learning problem. So input output pair is given to us, right? So we will use input output pair to make prediction, right? So again, here we are using fit function, right? So fit function, what this fit function will do, the fit function will fit a linear regression model using the data that we are providing here, right? So the training data we are giving here, housing prepared, this variable contain inputs, all inputs, right? And this housing label, this variable contain outputs, right? So output we are providing here and input we are providing in using this variable housing underscore prepare, right? Now in this variable there are several inputs, right? So it's not like that we are only providing one input and we are predicting one output, right? So we are predicting one output, right? Housing price we are predicting, but for that we are providing several inputs, right? Several features we are providing. So you can think this variable contain a table where there are roughly 16,000 rows because total 20,000 data points are there, 20,000 rows are there, and we have divided that 20,000 into two parts, right? So roughly 16,000 we are having in the training set. So 16,000 rows are there and several columns are there, right? So this variable contain a table, right? Okay, any doubt in this code? Okay, so this fit function will fit a linear regression model using this data, right? And now we will make predictions, right? So here to make predictions, we will use dot predict method, right? Linear regression dot predict because uh, this linear underscore rig is nothing but the model, our model, right? Because we are using linear regression model. Okay, so first we have fitted a linear regression model using the data set that we have prepared, right? Now we will make predictions using predict method, right? So this predict method, you can think in some sense it is similar to transform function, right? Because yesterday we saw two functions, right? Fit and transform function. So here you can think this predict is similar as transfer function in some sense, right? Okay. So here, what first we will do, we will first fetch data if we want to make predictions. So here ILOC is nothing but a method to get data from the indices that we are providing. So here we are writing :5, which means we want 5 rows, right? So this sum underscore data variable contains 5 rows data, right? Okay. And then housing labels dot ILOC again will give us the data for corresponding house prices, right? So for example, let's say we are selecting some rows and there will be one more attribute, housing price, which is the output label in our case, right? So we also want output labels, right? So for that, uh, we are using housing underscore labels dot ILOC, and this indexing we are doing to select 5 tuples, right? Okay. Then here we are using uh, some transformations because we have used several transformations, right? What transformations we have used? Missing out, filling out missing features, right? So if we have any attribute for which we are having missing values, we will fill out those missing values, right? So here in full pipeline, we have defined several operations, right? So first operation was missing values, right? So we are imputing missing values, right? Then feature scaling, right? So we have also used feature scaling, right? So all those operations we will do in this step, right? Full pipeline dot transform. Yes. So first we are imputing missing values. Then if we want to add any new attribute, we can add using combined attribute adder class, and it's a custom class that we have created to add new attributes. And then in the last step we are doing feature scaling, right? So these all steps we are doing for numerical attributes, right? For categorical attribute, we are doing, we are converting categorical values to some one hot encoding vectors, right? So these two steps, or you can skip this first step because this first step is doing nothing but the converting pandas data frame to NumPy array, right? So and in fact nowadays the latest version of scikit-learn doesn't require this step, right? So if you are using the latest version, then you can skip this first line, right? Okay. So here for categorical features, we are converting categorical feature to some numerical representation using one-hot encoding, right? And here for numerical features, what we are doing, we are first imputing, and if there is any missing values, and if we want to add some new extra attribute, then we can also do that. And then in the last, we are doing feature scaling, right? And then in the full pipeline, we are executing these two pipelines combined, right? So we combined num pipeline, which is we have created for numerical features, cat pipeline, which we have created for categorical features, right? So for numerical features, we are doing these steps. For categorical features, we are doing these steps, and then by in full pipelines, we are combining these two pipelines, right? So when we transform, when we execute this full pipeline, all these steps will take place, right? For numerical features, these steps will take place, and for categorical features, these steps will take place, right? So we are preparing our data to train a machine learning model, right? So we are pre-processing our data in some sense, right? Yes. So this full pipeline dot transform will do all transformations, right? So we have two types of features, categorical features and numerical features. So it will apply the transformations that we have defined, right? And then we will make predictions. So using this predict method, we will pass inputs, right? So some underscore data contains inputs. So we will pass inputs to our model that we have just trained, and it will give us the predictions or house price predictions as an output, right? If we want to print the actual values, we can also print the actual value, because this label, this variable, some underscore labels contains the actual data, the actual label, right? Actual output label. So if we want to print the actual output label, we can print using this variable some underscore label, and for model predictions, we can use predict method, right? So any doubt in this code? Okay, so here using this predict method, we can make predictions, right? Okay, so this is the result if you use this linear regression model, right? Okay, so since here we are taking 5 samples, we are making predictions for 5 data points. So there are 5 results here in this table, right? So this is the actual value, this is the predicted value, right? So as you can see here, we are getting errors, right? Some errors are positive, some errors are negative, right? So predictions are not exactly same as the actual values, right? And even in some cases, we are getting approximately 25% error, right? Okay. So here, to get the average error, directly we cannot sum these errors, right? Because some errors are positive, some are negative, so it will cancel out, and it may reduce, it may so you may get the wrong result, right? So for that, what exactly we will do? We will either use the squared error, or we will use the absolute error. We will only consider the magnitude of error and not the sign, right? Okay. So this is why we are here calculating RMS error, root mean square error. So either you can take root mean square error, or you can take mean square error. Uh, both you can take, right? Okay. So in regression models, uh, here we were calculating root mean square error on complete training data, right? So for that, we will use mean squared error function of scikit-learn, right? Yes. So here, first we will import mean square error uh, from scikit-learn.matrix, right? And after importing this method mean underscore square underscore error, we will pass 2 inputs. So here housing underscore label is the actual label, and housing underscore predictions, uh, this variable contains the model predicted values, right? Yes. So here this lean underscore rig dot predict, this output is nothing but the model predictions, right? And this output housing labels dot ILOC, this variable contains the actual label, actual output, right? And this is the model predicted output, right? Okay. So here we will pass uh, two variables. One variable contains actual labels, other variable contain the model predicted outputs, right? And this function will calculate mean squared error between the actual values and the predicted values, right? Yes. So here this variable contain mean squared error, and since we want to get the root mean square error, so therefore here we are doing square root, right? Because we want root mean square error. So this lean underscore MSC contain the mean square error. Since we want to root mean, so therefore we are doing square root operations, right? So after this operation, we will get this value. So here the root mean square error is 68628, right? And in these calculations, we are taking the complete training data, right? So the training error is this. The total training root mean square error is this, right? So it is the uh, root mean square error when we use the complete training data, right? And yes, this is the it is the mean error, right? So it's not the total error. So it's a total error when we use the complete training data, but again it's a mean, right? So first we will calculate square using actual and predicted value, then we will compute the mean, and in the last step we will use the square root, right? So it's a mean error, right? Any doubt in this code? Okay, so this root mean square error is high, right? So this is clearly not a good root mean square error, because we are getting a big number here, right? And for most of the district or most of the region, median housing value ranges from $120,000 to $256,000, right? So considering the median housing price in this range, this error is not acceptable, right? Because this is the error that we are getting on the training data, right? So typical prediction error of this is not so good, right? So now there can be two cases: either underfitting can be the problem or overfitting can be the problem, right? So this error, this big error we are getting on training data, right? So therefore underfitting can be the problem, right? Because in overfitting, what will happen in case of overfitting? The training error or the training error is low, or what you can say, the training performance, the training accuracy is high, right? Training accuracy is high or training error is low, and at the same time the test accuracy or the validation accuracy is poor, or validation error is high, right? So if we are having overfitting problem in our model, then the training accuracy will be high. So training accuracy is high means the training error is low, right? So training accuracy is high means training error is low, and at the same time the test accuracy will be poor. Test accuracy will be low. So test accuracy will be low means the test error will be high, right? But in underfitting, the training accuracy will be low, right? So training accuracy is low means the training error is high, right? So since here we are getting high training error, which means underfitting can be the problem, right? Now, how can we solve this problem? How can we fix this problem? Hello, am I audible?
We can choose a better model.
Yes, we can choose a better model because here we are using a linear model. So it may possible that the linear model is not able to capture the pattern present in our data, right? So this may be the reason for getting high training error, which means uh, the model is not able to capture the pattern present in the data, right? So for that, what we can do, we can select a more powerful model, right? Okay. So now we are training a decision tree regression model, and this decision tree regression model is a non-linear model, right? So in previous case, we used a linear regression model. So this linear regression model captures a linear relationship between input and output, right? But this decision tree is a non-linear model. So this model can also capture the non-linear relationship between input and output, right? So now we are training a non-linear model, right? Yes. And yes, we can provide a better features to the training algorithm. But here, since the training data is fixed, so we are proceeding with the first option. We are training a more powerful model, and here in this case, we are training a non-linear model, right? Okay. So this decision tree regression model is capable of finding complex non-linear relationship in the data, right? Non-linear relationship in between inputs and output, right? And decision tree we will cover in more detail later in this course, right? Okay. So this decision tree regression model we can import using scikitlearn.tree, right? And then we can fit a decision tree regression model using the data that we have prepared, right? So again, we are providing here the input values and the output values. So housing underscore prepared, this variable contains input values, and housing underscore labels, this variable contains the output value, right? Input output, because we are doing supervised problem, we are solving a supervised learning problem. So we will provide input output pair, right? So this first variable is input, second variable is the output, right? Okay. So this will fit a linear tree regression model using the provided data, right? Using the given um, training data, right? Okay. Now again, we will calculate error, right? So what we will do, we will again use the predict method. So predict method will predict the output uh, given by uh, given by decision tree regression model, right? So tree underscore reg is here our model, and we are using decision tree regression, right? Okay. So using the trained model, we will make predictions, and to get the prediction, we will provide here the again the complete training data. So this how to underscore prepared is nothing but the variable that contain inputs for complete training data, right? So this variable is nothing but a table, right? Which contains approximately 16,000 rows and several columns, right? Input. So because in input we are having several input variables, right? Okay. So here we are calculating the total error, total mean square error, root mean square error for complete training data, right? Okay. So here in input we will pass the complete training data, and we will get predictions, right? Now we will use the actual value, actual output labels. Housing underscore label is nothing but the actual output label, right? This housing label is nothing but this variable is the input variable, output variable. So this output variable contain the output label for complete training data, right? Okay. So here we will provide the actual labels and the predicted label, and the labels that we are getting using our trained model, trained machine learning model, right? So it will calculate the mean square error, and then to get the root mean square error, we will use square root function, right? Okay. So here, as you can see in output, we are getting zero root mean square error, right? So you can think how complex this model is, right? So this model is very powerful, and here we are getting exactly 0 root mean square error, right? And here we are using squared error. So it's not like that positive or negative error will get cancel out, right? And still we are getting 0 output error, right? Root mean square error. Now here overfitting problem may be there, right? I am not saying this model will suffer from overfitting problem. It may suffer from overfitting problem. It may not suffer from overfitting problem. We don't know because we have only tested the training accuracies, the training errors, right? And since training accuracy here in this case is the 100%, which means our model is able to 100% predict the price, right? Or in other word, the training error is 0, right? So overfitting may be there, may not be there. For that, we have to check the validation performance or validation accuracy or validation error or test error, right? Test error, test performance or validation error, validation performance, we have to check uh, to say anything about the overfitting issue, right? Because directly we cannot say that, right? So here we are getting 0 error, which means we are getting high training accuracy. But using this model, if we are getting a poor training, poor testing error, poor testing accuracy, or poor or high testing error, then only we can say that our model suffers from overfitting problem, right? So training accuracy is high, but test accuracy has to be low. Test accuracy has to be poor. Then only we can say model suffers from overfitting problem, right? Okay. So first part is complete. Model may suffer from overfitting problem, may not. We don't know. For that, we will check either validation accuracy or test accuracy, or validation error or test error, right? Because if error is high, then performance or accuracy will be low. If error is low, then accuracy or performance will be high, right? Okay. So here, since we are using a highly complicated model, so therefore, this model is absolutely perfect, right? And it may overfit the training data, but for that we will use the validation data or the test data, right? So now we will evaluate the decision tree regression model performance using cross validation, right? So cross validation I have already covered, right? So I will briefly go through cross validation, right?
Can you
So
please go to previous slide?
hmm, hmm, hmm.
So here you mentioned this is called overfitting the training data.
No,
So
no,
how?
but directly we cannot say that, right?
Yeah.
Because you are getting, let's say, you are getting a very good accuracy, a very good training accuracy, right? But when you check the same model on validation data or the test data, and there also you are getting very good accuracy. So do you think we will say this is the overfitting problem? No, our model is strong enough. Our model is generalizable. Model is working perfectly fine on the training data, and model is also doing perfectly fine on the test data. That's exactly what we want, right? We want that type of model only. We want good performance on the training data. We also, at the same time, we also want good performance for the future data, right? This is what we want, right? So, but yes, in this case, since we are getting 100%, so 100% is doubtful, right? We cannot get the 100% data over 16,000 data points, right?
Yeah. So then we should say this may be overfitting, right? We can't say this
Yes,
is.
yes, yes. It totally depends on the validation data or the test data, right? So without checking the validation set accuracy or test accuracy, we cannot say anything, right?
Yeah.
Okay. So for that, we will use cross validation, and cross validation I have already covered. So in cross validation, what exactly we will do? We will divide the training data into into two parts, the training part and the validation part, right? Because we cannot touch test data. We cannot make any decision using test data. Test data or test set is totally reserved for the future purpose, right? Because we want test data to be a good proxy of future data. We are creating these model to make predictions for future data and not the present data, because present data we already have the output labels, right? We already know the ground truth. We already know the actual values for the given present data, right? So using present data, using training data, we will train our model, and we are building these models to make predictions for the future data, right? So to ensure that the test data is a good proxy of future data, we will never take any decision using test data, and we will only reserve test data as a future data, right? We will think that test data is the future data, and we will check model performance uh, using test data after completing all steps, after taking all decisions, right? So, or in other word, you can think we will not take any decision using test data. Test data we will only use once to check the final model performance, right? So now the training data we cannot also use, right? Because the training data we already train our model, right? We already train our model using training data. So model has seen training data. So therefore, training if we take decisions using training data, uh, we may get the wrong result, right? Because the model has already seen the training data. Now to overcome this problem, we are again dividing the training part into two parts, and that process is called the cross validation, right? Yes. So test data we cannot use. Test data we will use only for the final model, right? We will not take any decision using test data, because test data is we are considering as a proxy for future data, right? So we will again divide training set into two parts, a smaller training set and validation set, and we will use this validation set to make any decision. If we want to decide anything in the model, we will use validation set accuracy, right? We will not use the training set, because using this training set we are training our model, we are training our machine learning model using this training set. So model has already seen this training data, right? So if you use the same set to decide anything, so for example, you are calculating you are changing some parameter values and you are checking accuracy using training set, or error using a training set, uh, you may get the uh, wrong ideas, right? Because training data model has already seen, so it may possible, depending upon your model complexity, it may memorize the complete training data, right? As we saw in this case, here the model has memorized everything, right? Model has memorized the noise present in the data, model has memorized and everything, right? Every pattern present in the data. So that's why we are getting perfectly zero error, right?
So,
Yes.
just like we divided our original data set into training and test using usual standard, say
Mhm.
70-30 or 80-20, right? What
Mhm.
is the criteria that we divide training data set into the training and validation in usually in the industry?
Yes, yes. So here also we can use 80-20. So or 90-10 sometimes we also do. Right. So let's say out of 80% of training data, we can use again 80% for smaller training set and 20% for the validation set, right?
Okay.
And this smaller training set now we will use to train our model, and this validation set we will use if we want to decide any hyperparameter, any parameter uh, on which the model performance depends, right?
Yeah.
So if you want to decide something in your model, you will use this validation set. So this is the purpose of this validation set, right? And what people generally do, so let's say you are training a model, and to train that model, you have to decide 5 things, right? 5 things can be anything depending upon what type of model you are using, because in every machine learning model we have to decide some parameters, right? So to make those decisions, we will use validation set. So what exactly we will do? We will select first options and train our model using this data, and now we will check this model performance using this validation data, right? Because we are only training our model using training data, so we cannot use this data to check the performance, and therefore we are using validation set data, because validation set data we are not using in model training, right? We are validation set data we are only using to check the model performance, to check the model error, right? For evaluation we are using this validation set, right? So we are not training using validation set, we are only training our model using training set, right? Okay, so suppose you want to decide some parameter, and that parameter may contain 3 values, right? So you are having 3 options. So what you will do, you will first try option 1, and you will train your model using training set, and then you will check validation accuracy or validation error, right? Then again you will try option 2, you will again train your model using same training set, and again you will check the validation accuracy or validation error. Now again what you will do, you will try option 3, you will train your model using training set, and again check the validation accuracy or validation error. Now you are having 3 options and 3 validation accuracies or 3 validation error. So depending upon this validation accuracy, you will pick the model that using which you are getting the highest validation accuracy or lowest validation error, right? So you will pick that model. So model selection here you are doing using cross validation, right?
So 3 options means you are saying 3 models like descent tree or render forest, 3 different models we will run on a smaller data set and then
Yeah, that can also be do. So here in the decision we can have several types of options. So for example, let's say what you can do, you can pick different you can pick models from different model class. So for example, one model is linear regression, another model is support vector machine, another model is decision tree, right? So this type of selections you can also do, and within one model you can have several options. So for example, in decision tree there are several parameters. So for example, depth of a tree, or number of leaf node, and several more I will discuss when I will cover decision tree. So in each model we are having several other parameters also. So there also you can select the correct value of parameters using this method, right? So both you can do, either you can select a model across different model class, or within same model class, within the same decision tree, you can select the correct value of hyperparameter, correct value of parameters, right? Okay, so sometimes what people generally do, so let's say after using cross validation, now you know that the option 3 is the better option, right? If you use option 3, then you are getting highest validation set accuracy or lowest validation set error, right? So now we already know that option 3 is better than option 1 and 2. Then what you can do, you can simply take option 3, and now you can train your model using complete training set and directly check its performance using test set, right? Because now you already know option 3 is better than option 1 and 2, right? A priori we don't know. A priori we are having 3 options and we don't know which option is the best. So to check option 1 is the best, or option 2 is the best, or option 3 is the best, what we can do, we can further divide training sets into 2 parts: smaller training set, validation set. And using this validation set, let's say somehow we got to know that option 3 is better than 1 and 2. Now we already know option 3 is the best. So therefore, what we can do, we can use, now we can proceed with the option 3 and use this complete training set to build our model. So that options also you can do, right? So it's not like that. You always train your model using smaller training set. So suppose sometimes if you are having um, uh, if you are having the data set where limited samples are there, right? So if you do this type of division, so you are further reducing the size of data set, right? Because learning model performance totally depend on the data quality and the number of samples, right? If you are using very few samples in training machine learning models, the performance uh, will not be so good, right? Okay, so any doubt in cross validation?
In our case, we have only divided into training set and test set only, right? We have not divided into validation set in the initially. So how can we do that? We have already done 80-20, right?
No. So scikit-learn package is there. Directly we will call that package, and it will automatically divide training, test, and the validation set, right? And in fact, there are several strategy to divide original data set into two or more than two parts, right? So it's not like that we will divide we will divide the data set in randomly, right? So and yes, we will mostly use stratified approach, right? Because if we are having imbalanced classes, so let's say if 99% class 99% class 1 samples are there in our data set and only 1% data set belongs to the class 2, then if you do random division, if you do random selection, then it may create problems, right? So then in that case we will use stratified approaches, right? Stratified approach I have already covered, right? Okay, so this training set now here one more problem is there. It may happen that you are unlucky and this split is not so good, right? Which means we are considering this validation set as a proxy for future data, right? Because we are taking decision using this validation set, right? Isn't it? We are making decision using validation set by thinking that validation set is a good proxy for future data, right? What if this condition is not true, right? It may possible that since you are let's say you are doing random division or whatever division policy you are doing, and in that case after dividing, this validation set is not a good proxy of future data, not a good proxy of test data, so therefore your decision may be wrong, right? So to overcome that problem, what we will do, we will do this division multiple times, right? So as you can see here, we are now dividing training data into two parts 10 times, right? So here, this is the first division, right? This is the second division, third division, and this is the 10th division. So we will divide the training data multiple times into two parts, training part and the validation part, right? So for the first iteration, suppose assume this is the validation data, right? So here we are dividing the training data into 10 parts, right? So roughly we are taking 90% of data is a training data and 10% of data is a validation data, right? Okay, so last part we are considering as a validation data. In the second iteration or the second round, we are taking the second last mode part is the validation data. Similarly, here third iteration, third last part we are considering as a validation data, right? So as you can see here, in each iteration or in each fold, we are using different training data and different validation data, right? So here this is the validation data in the second round or second fold. This is the validation data, right? So in each fold, we are using different training data and different validation data, right? Now, the benefit of this multi-fold cross validation is you may be um, unlucky, let's say for this first division or second division, but since we are dividing it multiple times, so very low probability is there that you are unlucky in each and every uh, fold, right? So this is why we are not relying on first division, and we are dividing. We are doing this division multiple times, right? Okay. Now you will compute error using the. So what you will do? You will apply the same process. You will use this smaller training set to train your model, and you will calculate model accuracy or model error using validation set, right? So here in this case, you will train your model using these using these training data, and you will test your model performance using validation data, right? So let's say the performance or error of the model is even when you use this portion as a validation set, right? When you use this portion as a validation, this is the error. So likewise, you will get 10 errors, right? Because you are training model 10 times, right? First time you are using this data to train your model, and you will use this data, this portion of data to validate your model, right? Because now this is the validation set, right? Okay. So you have calculated error, and now you will get the average error, right? So this because and this process is called the 10-fold cross validation, because you are making this division 10 times, right? If you do this division, let's say 5 times, then that process is called 5-fold cross validation, right? So in k-fold cross validation, we will do this division k times, right? Okay. And finally, what we will do, we will calculate the average error, right? So we are not directly relying on one partition, one division, and in fact, we are relying on the k partitions, right? We are calculating average error or average accuracy using k divisions, k partitions, and this process is called k-fold cross validation, right? Okay, so this slide I have already covered. So yes, we will use train test split function of scikit-learn to make these divisions, right? Yes.
Um, Praveen, can you just explain once more, like this training part, you're splitting k times k fold, but the same training set. Okay, if I say, can you just explain it once more? Maybe I
Yes. So
wanted
assume
to frame the question.
this is your the training part, right?
Hmm.
Now you're dividing the actual training data in the two part, training part and the validation part. So this is the training part and this is the validation part. You will use this training part to train your model, and you will calculate model performance using validation data, right? Now again, in the second time, you are dividing the training data set into two parts, training part and the validation part. But now this validation part is different. This validation part is different from this validation part, right? And this training data is different from this, because you are making divisions using, you are making different divisions, right? And again,
Okay,
you will
so
yes,
same model is being trained k times,
k times
like that.
from scratch. Same model is being trained k times from scratch, right? So from
Okay.
scratch, we will use this data as a training data and this data as a validation data to test our model. The same model we will train again from scratch using this training data, by considering that this is our training data, and we will check its performance using this validation data. But here, this validation data is different from the validation data that we have for the previous split, right?
Okay, got it.
Yes. So here we are splitting data set into 3 times. So therefore, this scheme is called 3-fold cross validation, right?
So what is the ideal way? Is it 3-fold or 5-fold or 10-fold? What
No,
is
no,
that we
it depends
usually use?
upon our problem. Sometimes people do the 5-fold cross validation or 10 times cross validation, because since you are doing, you are training your model multiple times. So if your model is computationally expensive, then generally we will do 3-fold or 5-fold, because you are training model 3 times, right? So, but let's say if the data set size is small and the model complexity is not so high, then you can go up to 10-fold, right? Because if you are doing 10-fold cross validation, then you have to train model 10 times, right? So it will increase the training time, right? It will increase the computational cost. Yes. And finally, what we will do, we will return the average error, right? Because since we are dividing training data 10 times, right? So we will get error. We will train model. We will train our model from scratch 10 times. And for model 1, we will get some error. Model 2, we will get some error. Model 3, we will get some error. Likewise, we will have 10 errors. And finally, we will calculate average error. And now we will decide using this average error, right? Okay. So if you want to do this split manually, if you want to do this process manually, then you can use scikit-learn train test split function. And scikit-learn train test split function will partition the data set into to multiple parts, right? Or directly you can use scikit-learn's cross validation feature, and that automatically do all this process for you, right? We don't have to do uh, anything manually, right? Only you have to call this cross validation. You have to import a cross validation from scikit-learn.model selection, and here you have to mention CV is equal to 10. If you want to do 10-fold cross validation, if you want to do 2-fold cross validation or 3-fold, here you have to mention CV is equal to 3, right? And it will automatically do uh, this process for us, and it will report the average error or average accuracy using 10 folds. If we are doing CV is equal to 10, if we are doing CV is equal to 5, it will divide 5 times and it will report the average of 5 error, right?
So it will divide training data set into a small data set and validation data set, or it will divide the original data set into 3 parts?
No. The test part it will not touch. It
Okay.
will only divide the training part, and it will report the accuracy or error using the validation data, right?
Okay. So to divide original data set, we will still use the scikit-learn only, right? That is the only method to divide.
No. We will use this. We will use cross well score, right? And this cross well score will automatically do cross validation for us.
But that will do only for the training data set to divide into smaller training and validation, right? For the original data.
No. Actually, here, yes. So if you see, we are first importing cross well score, and then we are passing here the model. So because we have to pass here some model, right? So since we want to do cross validation using decision tree model, so therefore here I am writing tree underscore reg, right? Tree underscore reg is nothing but the uh, decision tree model, right? Decision tree regression model, tree underscore reg. So this is the model using which I am doing cross validation, right? Now this housing underscore prepare is the variable that contain training data, and housing underscore label is the variable that contain the output labels for training data, right? So this model, this method doesn't know anything about the training data and test data. It will divide the the data that we are providing. But here housing underscore prepared, this variable contain only the training data, right? Are you getting my point? So this is the variable where we only have the training data, and this is the corresponding output label. So it will divide the data that we are providing, right? And
So-
it will do 10 such divisions, because here we are writing CV is equal to 10, right?
So it will divide only housing underscore prepared data, it will not touch anything on the housing underscore label, right?
No. Housing underscore prepared, this variable contains the training data. If you pass here the variable that contains the complete data, then it will divide the complete data, right?
Okay.
So this method doesn't know anything about the training set or the test set. Whatever data we are providing, it will divide the data into two parts. So this is why here we are only providing the training data, right? So housing variable, this variable, yes. So this variable, housing prepared, this variable only contain the training data, right?
Yeah, got it. So I was asking that as a practice, we should provide here in this
Yes,
function.
so we should always provide here the training data and not the complete data.
Okay.
Because if you provide here the complete data, it will divide complete data into two parts, right?
Mhm.
Because we
So-
want 3 divisions, we don't want 2 divisions, right?
Yeah.
So for that, yes.
Still we will provide into the scikit-learn train test function only, right? The original data.
Yes. So train test, it will create two split, training and testing. And in fact, we will use stratified approach, right? Stratified approach to get the training data and the test data, and then the training data we will provide here. It will make further divisions, and it will do the cross validation, right?
Yeah, got it.
Now,
Question.
yes.
So we are using different training sets, so it will generate 10 different models.
Yes,
Is
it will generate 10 different model. Now,
Yeah.
it
So
may be
how?
the case when you are passing, when you are checking, let's say, 10 options for the same model class. So, for example, let's say now you want to check 5 options for the same decision tree model. It will train decision tree model 5 times from scratch, where in each iteration, in each round, you are using one options, right? So let's say option 1 you are first trying, then option 2 you will try, option 3 you will try. So likewise, it will train your model 5 times, because you are testing 5 options, right?
Okay. So how? Which model to use if we generate 10 models? So if there are 10 models, then how we will decide which model to use?
No. It will it will return the average error,
Yes.
right? So yes, so this cross validation is only for when you want to decide something, right? So what you can do here, let's say you have 3 options, right? So model 1, option 1, you will you will you will do this split. Model 1, option 1, you will train model 1, option 1 10 times,
Okay.
and you will get one average error. Then model 1, option 2, again you will train from scratch 10 times, again you will
Mm.
get one average error. Model 1 option 3, again you will 10 times and you will get average error. So indirectly you are training a model 30 times if you are using 10-fold cross validation, right? Because model 1 option 1 you will train that model 10 times if you are using 10-fold cross validation, right? Now since you are having three options, option 1, 2, 3, and you want to try out all three options, so indirectly you are total you will train model 30 times, right? Now model 1 option 1 you have one average error or average accuracy. Model 1 option 2 you will have another average error. Model 1 option 3 you will have another average error or average accuracy. You will decide best model out of these three models for which we are having highest average accuracy or lowest average error, right?
Yeah. Got it.
So we are not having 10 models. We are having three models because we are testing out, we are exploring three possibilities, right?
Mhm.
Now in each case, we will train model multiple times because we are using multi-fold cross validation. We don't want to rely on one split, and rather we want to rely on average of different splits, right? Because this split can be unlucky. Here, if we are training our model using this data and we are testing our model using validation data, here the assumption is this validation data is a good proxy for future data. We are thinking that this validation set is a future data, right? But this condition may be true or may not be true. So to ensure that condition, we don't want to take risk, and we are making this division multiple times so that on an average, the assumption may true that this validation set is a good proxy for future data, right? Because one time you may be unlucky, another time still you may be unlucky, but if you are repeating this process several times, very low probability is there that this validation set is not a good proxy for future data. So this is why we are repeating this process multiple times, right?
Thank you.
And one point you can note here, I'm using negative mean square error. So can you tell me why I'm writing here negative mean square error and why not just use mean square error? Because in previous examples, I'm using mean square error, right? Mean square error function, root mean square error function to get the error. But here in cross validation, I'm using negative mean square error. Yes. So actually, this cross validation score is designed to maximize something, right? So here this scoring variable, whatever we will write here in scoring, it will give the best result that maximizes this, right? So this is the property of this function. This function we have designed in this way, right? It will give you the best model, or it will select the best model that maximize this score. So here, if you write accuracy, scoring is equal to, let's say, you can also write here accuracy. So it will give you the model that maximize that is accuracy, right? But since here we are writing error, so what exactly we want? We want a high error model or we want low error model? Because it will test
Error.
low error model, right? So now to get the low error model, but yes, it will always pick the model that maximize this score. So therefore, we are putting here the negative sign, right? So can only be greater than equal to 0, right?
Yeah.
Because it's a mean squared error.
Yeah, correct. So it will take the lowest
Yes.
error.
So error
Or-
can be greater than equal to 0, right? Now assume we are having several possibilities of error, right? So let's say for one options we are having 5 error, other options we are having let's say 1 error or a 0 mean square error, right? Since we are putting negative sign, so -5, -1 and -0, which is nothing but the 0, right? And it will pick model that maximizes this score. So here the maximum value is 0. So it will pick model that that is giving the 0, because 0 is the maximum value after putting negative sign, right? And let's say if 0 is not there, if you are having let's say 5 error, 3 error, or let's say 2 error, right? So these and when you put a negative sign -5, -3, -2, so here after putting negative sign, which value is the highest value? -2. So -2 is the highest value. So indirectly it will choose the model that is producing the lowest error, right? By selecting this highest value, you will get the model that is having the lowest error, right? Because here we have put the negative sign, right? So if mean squared error is low, negative will be the highest, right? As you can see here, this 2 is the low value, but the negative is the high value, right? So any doubt here? Why we are using here negative mean squared error and not the mean squared error? If you write here simply mean squared error, then it will give you this model that is having 5 error, right? Because it will always select model that maximize this score, right? Okay, so it will since here we are using cross validation is equal to 10, so it will divide 10 times, and it will calculate, it will use it will train model 10 times, and it will give you the average score, right? Okay, so now if you want to print the score, you can use in fact you can print the mean of score, standard deviation of score, because here since we are using cross validation is equal to 10, so it will train 10 models, right? So what you can get, what numbers you can calculate using these 10 errors? You can calculate mean, you can calculate the standard deviation, right? So here I am calculating average error. So average error is nothing but the mean error, right? So this is the mean error, and in fact, since we are having 10 error, because we are having 10 different models, so we can also calculate the standard deviation, right? Yes. So this mean is nothing but the average error, and this score, since we are using cross validation is equal to 10, so this is the first model score, this is the second model score, this is the third model score. Likewise, we will get 10 score values, right? And this is the mean score, and this is the standard deviation score, right? Okay.
So this score is the error that the minimum error
No,
that
no.
we,
So the score is this value.
yeah. So from each iteration, one score we got, no?
Yes, yes, yes. So this is why we are giving we are here getting 10 scores, right? One score for first iteration, second score for the second iteration. So total 10 scores are there, right?
And this score also is the average value, no? Because in one iteration it will run 10 times, right?
No, 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 no.
In
One
each,
iterations we will train model one time. The only difference is we will use these cell as a training data, and this particular cell is a test data or validation data, right? So this is our validation data. In second iteration, now we will use this data, this portion of data as a validation data, and remaining data as a training data, right? So one time we will train our model in iteration one, iteration two, again we will train our model um, using using different training data, and we'll test our performance using this validation data, right?
Okay, so each iteration we are changing the validation data set.
Yes, in each iteration you can think we are changing the training data and the validation data. So this set is different in each iteration, and this set is also different in each iteration, right? Or in other words, in each iterations we are making this division differently, right? We are dividing training sets into two parts, and this division is different in each iteration. And now we are using this part to train our model, and this validation set to evaluate our model, right?
So each iteration, we understand that we are changing training data set, or splitting the training data set multiple times. But in each iteration, we are changing the model as well, like decision tree or SVM, or we are first.
No, so we can do both. But for the sake of simplicity here, we are using the same model, right?
Got it.
Yes. No. But here, if you are writing cross validation is equal to 10, then in each iterations you will use the same model, right? Now let's say you are testing three different model. So for model 1 you will have 10 iterations. For model 2 again you will have 10 iterations. For model 3 again you will have 10 iterations, right? So model 1 you will train 10 times and you will get average error. Model 2 again you will do this 10 times and you will get the average error. Model 3 again you will do repeat the same process, right? Or it can be model 1 option 1, model 1 option 2, model 1 option 3, or it can also be model 1, model 2, model 3, where all three models are different, right? And in each model or in each options you will train that options or that model 10 times if you are using cross validation is equal to 10. If you are using 10-fold cross validation, then you will do this division 10 times, right?
Yeah. And this CV is equal to 10, we get this through trial and error, or?
CV is equal to 10 means you want this division 10 times. You want to use 10-fold cross validation. If you want to make, let's say, 3 iterations only, then you will write here CV is equal to 3. Then it will do this division 3 times only, right?
Yeah, that I understand, but I'm asking that how we reach to this number. It will be 3 or 5 or 10.
Again, it's a hyperparameter, so we don't know this number.
It is hit and trial.
Yes, a hit and trial, but we know the fact that if we do this division 1 times, then definitely we cannot be so sure. So we have to make these types of divisions multiple times. Then only we can decide some parameters. So we can make some reliable decisions using this validation thing, right? Because using one split, one iterations, we cannot make a reliable decision, right? Because we may be unlucky. We may be unlucky that this validation set is not a good proxy of for the future data, right? And to overcome that problem, we are not relying on one split, and in fact, we are relying on multiple splits, right?
Got it.
Okay, so since we are using 10 iterations, so therefore we will get 10 score values, right? And we can get the mean value, we can get the standard value. The same process we can repeat for the linear regression model, right? So you can use the same function that we have used here, cross val score, to do the cross validation for linear regression model, right? So now we are passing here the linear regression model, the training data we are providing here, the corresponding output label we are providing here, and again the same error metric we are writing here, negative mean square error, and again we are doing 10-fold cross validation, CV is equal to 10, right? And these are the scores, 10 scores, because we have to train the same linear regression model 10 times because we are using cross validation is equal to 10. We are doing 10 splits, right? 10 times we are dividing data into two parts, training data and the validation data, right? Okay, so these scores we are getting in case of linear regressions, right? So again, this is the mean value and this is the standard deviation. So if you compare these two models, linear regression model and decision tree regression model, so as you can see here, and by the way, these scores we are getting using validation data and not on the train data, right? So this is the mean value that we are getting using validation data, right? Yes. So yes. So here we are getting 68628 error, this root mean square error over complete training data, right? So training data, if you use complete training data, this is the error that we are getting in linear regression, right? So this error is not on the validation data, right? Because we have not divided training data into two parts, training and validation. And here we are using only the training data, right? So we are calculating mean squared error using the complete training data. So this is the training error, right? When we use the complete training data, this is the root mean square error that we will get using complete training data, right? Okay. Then we calculated the training error using decision tree regression model. So when you use decision tree regression model, we are getting zero error, zero root mean square error for training data, complete training data, right? Now we further divide the training data into two parts, training part and the validation part. And we are not using this validation set in the training. We are training our model using training part, and this validation part we are only reserving for evaluating our model, right? Here, the difference is we are calculating model performance over the same data that we are using as a while training our model, right? So this zero is the root mean square error using the same data that we have used to train our model, right? And here the difference is we are not using this data in model building, in training our model. We are only training our model using this training set, and we are reserving this validation set for evaluating our model, right? So if we do this type of division, if we calculate validation set accuracy, these numbers we will get, right? So as you can see here, when we are calculating mean error, when we are calculating root mean square error for decision tree regression model, training data, over complete training data, we were getting zero error, but now we are getting 71,379 error, right? Which is again higher than the error one, right? So now can we say that this decision tree regression model is suffering from overfitting problem? Because training error is zero, but the validation error is high, right? So this number we are getting
Yes.
for validation set, right? And validation set we are not using in building our model, right? Okay. So as you can see here, the training error, the training root mean square error is 0, but the validation root mean square error is high, and in fact this number is greater than the number that we are getting for linear regression model, right? So what we can say here, this decision tree regression model, if we use the decision tree regression model, we are getting low or zero training error, but the validation error is not zero. Validation error we are getting very high value. So therefore, decision tree regression model is suffering from overfitting, and this linear regression model is suffering from underfitting problem. Why? Because here in this case, even training error is poor and the validation error is also poor, right? If you check training root mean square error for linear regression model, this training error is high, right? Training error is high, and at the same times validation error is also high. Validation error is also high, which means linear regression model suffers from underfitting problem. Decision tree regression model suffers from overfitting problem, right?
So did we use the same validation set for both the models to calculate the mean?
No, we cannot say, because it will split data set 10 times, right? So we cannot. So depending upon what type of scheme we are using. So for example, if you are dividing randomly, so in each iterations you will get a random split, right? So therefore, this average, and in fact this is the average error and not the error that we will get using the single iterations, right? Yes. So this is the average score, average error.
Yeah, but to decide which model is giving the underfitting or lower overfitting problem, we said we should fix our validation data set, then only we can decide now.
No. So overfitting of one model does not depend on the performance of other model, right? Underfitting and overfitting problem are with respect to one model only, right? So here we have seen two types of model: linear regression model and decision tree model, right? So in case of linear model, we are getting, yes. So by just checking performance of linear or performance of decision tree or error of linear, error of decision tree, we cannot say anything about the overfitting or underfitting problem, right? Here we are saying that this model, linear regression model, suffers from underfitting problem. Why? Because the training error here is high. The training error is high for linear regression, and the validation error is also high, right? And for decision tree regression model, why we are saying this model suffers from overfitting problem? Because here for the same model decision tree, the training error is 0, but the validation error is high, right? Which means this model has memorized everything. This model has memorized the noisy pattern present in the model. So that's why we are getting 0 training error, but validation error is not 0, and validation error is in fact high, right?
Okay, so cross validation function we use to decide whether the validation set is true, correct or not. So where we are doing that decision, because here we are doing decision like model, which model is giving the correct error, but where we are doing that validation data set is correct or not for us. That is not we are doing, right?
No. Can you repeat your question?
So this cross validation function we can use for both the things, no, for deciding whether which model will be selected or which validation data set will be selected, right?
No. So validation set this this function will do this split automatically, right?
So my question is, where we are deciding that whether the validation data set is correct or not for us in each model.
No, we are not deciding anything, because that's why we are doing 10 splits or 5 splits or multiple splits, because we don't know, we are not sure that this validation set is a good proxy for future data or not. We don't know. This is why we are repeating this process multiple times, right?
Yes. After repeating the process, we will take decision whether validation
We
data
will
set.
take decision using average error and not just using the E1 or E2 or E3, right? We will make decision using this average value.
Yeah. So in this example,
In this example, we are not deciding anything.
okay.
We are simply taken one linear model and one decision model, right? Here I have only explained the process of cross validation. The model selection or the hyperparameter tuning I have not covered, right? But for that also we will use the same process, cross validation. So you can think here or you can think here I am deciding, I am doing model selections. I have two model, linear regression and decision tree regression model, and I want to select the best model, right? So for that, after using this cross validation, now I end up getting the average error for linear regression model and average error for decision tree regression model, right?
Right.
And these are the numbers. So if you see these numbers, I will prefer linear regression model over decision tree model, because in this case, the average cross validation error is lower than the average cross validation error for decision tree regression, and this number is the mean, because this number is the mean of 10 error, because here we are using 10-fold cross validation, right? So we are taking average error of 10 models, right? Yes. The point that I am here discussing is that linear model here suffers from underfitting problem and decision tree model suffers from overfitting problem, right? Because now I have the training error and the validation error. And this is the beauty of cross validation, because if you directly decide using training error, then you will select decision tree model, because in case of decision tree, you are getting 0% error, right? So see, if you use linear regression model, you are getting 6 to 8 error, right? A high error you are getting, high training error you are getting if you use the linear regression model, right? But if you use the decision tree regression model, you are getting 0% training error, right? So if you only see the training error, then definitely you will choose the decision tree, which is a wrong decision, right? Because this model is capturing the noise present in the data, right? So ideally, you should not uh, decide only using the training accuracy or training error, right?
Yeah.
Because if you only use the training accuracy or training error, you will choose this model, decision tree regression, and future time this model is performing poor than the other options that we have, right? Because this model is not the generalized this model is not the generalized enough, right? Training time it is doing perfectly fine, but test time, future time, it is not doing so great, right?
Got it.
Can we generalize that decision trees are more prone to capturing noise as compared to other models?
Yes, yes. So I will discuss in decision tree is highly prone to overfitting problem, because decision trees are so powerful model that it can capture everything in the data, right? So it can memorize even the complete training data. So then if we are using decision trees, then we always use some form of regularization so that we can prevent the overfitting, right?
What do you mean by regularization? Is it removing the noise?
No, regularization. Here we will use to regularize our model so that we can prevent the overfitting problem. We can prevent the so see, since as you can see here in this examples, here we are getting perfectly zero error, right? So we don't want this case. So for that, what we will use, we will put some conditions while training our model so that it can avoid noisy pattern present in the data, right? So the detailed discussion I will do the we will have a detailed discussion when I will discuss the decision tree, right? But in broad sense, you can think here since we have not put any constraint in this in learning decision tree, so therefore it is this model is memorizing everything, right? But we can fix this problem,
Okay.
right?
We see that decision tree algorithm may still be an okay model for this problem, but we have not applied it properly.
Yes. Okay. So if you see the cross validation error, according to cross validation error, linear regression model is performing better than decision tree model, right? But still, we will not use linear regression model or decision tree model, because linear regression model is again suffering from underfitting problem. Decision tree model is suffering from the overfitting problem, right?
So when you say error is high for linear regression as well, so high means what? How much, from which benchmark we are considering? From the linear
No, we
regression?
cannot say anything because it depends on what we are predicting. So let's say if you are predicting a number in millions, then error will be definitely high, right? But if you are predicting a number in let's say 10 raised to power minus 5 order or 10 raised to power minus 6 order, then definitely error will be low, right? So depending upon our problem, depending upon what number we are predicting, the error may go. So that's why directly we will not say that this much error is better, this much error is not good, right? It depends on what type of problem we are solving. It depends on what type of variable we are predicting, right? So for example, let's say if we are predicting height, person height in let's say foot, the error cannot be 100, right? But let's say if you are predicting let's say if you are predicting um, weights, then you may get error beyond 10, right? You may or may not get, depending upon your model and the data quality, right? But in fit, 10 fit person is not there, right? Say 9 fit person is not there, so you cannot get that type of error, right? So directly you cannot say anything, right?
Got it.
Yes. So and for the same problem also, we are saying, yes, we are saying this error is high because the average, the median housing price ranges from $120,000 to $265,000. And considering the housing price lies in this range, we are saying this is the high error, right? Okay.
Yeah, got it.
Yes. Yes. So decision tree model performs worse than the linear regression model. So because in this model we are having overfitting problem, and here we are having underfitting problem, right? Okay, so we can use cross validation to estimate the performance of our model, and in fact we can use the standard deviation to measure how precise is our estimate is, right? Because as you can see here, we are calculating mean value and the standard deviation. So this standard deviation will tell us the uncertainty in our estimation, right? Because this is the mean value, and and this is the standard deviation. So if since here we are calculating mean and standard deviation, so therefore uh, we can also get some idea on how precise our estimation is, right? Yes.
So can you please elaborate more why we are calculating standard deviation? What help it will get?
No. So standard deviation is giving us the uncertainty present in our estimation, right? Or you can say the precision, right? So for example, let's say if we are having values, let's say 10, 10, 10, 10, 10, right? In this case, if you calculate mean will be the 10 and the standard deviation will be the 10, because we don't have any variation in our predictions, right? But if we are having a high variation in our predictions, then in that case, the standard deviation will be high, right? So as you can see here, one model we are getting 66782 score. The other model we are getting 74739. So this much variations we are having 2731. So this standard deviation is capturing the variation present in our uh, uh, error, right? Because these are nothing but the 10 errors for 10 different models that we are training 10 times, right? Because here we are using cross validation is equal to 10. So standard deviation is capturing the variation in these individual error numbers, right? So here, as you can see, the variation is more, and for decision tree regression model, the variation is less, right? So mean is high, we are getting high error, and variation among 10 error is less as compared to linear regression model. So generally, we will only consider the mean error, right? So since here the mean error is low, so therefore this model will perform better at the future times over the other model, decision tree regression model, right?
So the low variance variation or low standard deviation is good or high?
No. We will decide only using the mean value, because mean value what we care, but again the variation should not be too high. So it should not happen that for one model you are getting very high validation error, and for the other model you are getting very low validation error. That means there is some problem with our data, right?
Means if a standard deviation for both the models are very high compared to one model over the other, which means there is some problem in the data. Is it what?
Yes, there is some problem in the data, or maybe the split is not good. We should skip that split, right?
Okay.
Okay, so yes, so here I'm training one more model, random forest regression model. So random forest regression model is nothing but the collection of several trees, right? Because forest is a collection of tree, right? So decision tree, in decision tree method, we will train one model, but in random forest, we will train a collection of decision tree. right? So here we will use ensemble learning concept. So we will combine predictions from multiple model to get the robust predictions, right? But yes, this random forest model I will cover later. So here you can just think we are using one another machine learning model for the same problem. And here in this random forest model, it uses multiple decision trees to make predictions, right? But I will cover random forest in detail, right? Okay. So if you use the random forest model, so here if you again calculate the same error, so here for the training data, you will get 21941 error, which is lower than the error that we get in decision tree and in linear regression, right? So if you use the random forest model, and you will calculate the same error, mean squared error, you will get 21941 error. And if you use the cross validation, you use the cross validation again 10, and if you calculate the score, these scores you will get. And if you compare these three models, as you can see here, in case of random forest, you are getting minimum cross validation error, right? So therefore, the random forest performs better than the decision tree and better than the linear regression. So if you have to select one model, you will select random forest model, because random forest model is giving minimum cross validation error, right? Okay. And this random forest model, I will cover in detail later in this course, right? Okay. So we can select, we can train for the same problem, we can train multiple models, and using cross validation, we can select the best model. And here, what I mean by the best model? Best model means the model that is giving the maximum validation accuracy or minimum validation error, right? So as you can see here, this model is giving the minimum error. So therefore, we will select random forest model, and random forest model is the best model, right? Okay. Now the next part is fine tune the model, right? So here in fine tuning, what we will do, we will have sometimes we will, yes.
I have a question, a basic question on step number 5.
Mhm.
When we say please go to the next slide.
Mhm.
So where we had this process listed. Yeah, exploring the models basically.
Okay.
When we say we have to explore models, how do we go about this exploration? Because there are so many models available, and sometimes we may not even know the data very well if they have too many dimensions. So is there a structured approach or a process so that we can say which ones should we try out? How do we start?
No. So here, by visualizing your data or by visualizing the pattern present in the data, a priori we can filter out some models, right? So for example, if you have the non-linear relationship in the data, then why should I try linear model? I already know the linear model will not work great if my relationship is non-linear, right?
If there are hundreds of dimensions, let's say, and it's an unknown data,
Mhm.
then do you think visualization manually will be a practical step?
No, but then also we know that it totally depends on the problem and the data that we have, right? So in let's say in worst case, you have to check each and every model, right? But sometimes if you have if you have expertise, then you can filter out models by visualizing data, or by using the property of that model, right? So, but then you need an expert. Expert can do this, right?
So what is that expertise? Expertise, is there no process? Is there no structured approach, or is it just that
No.
we
So
keep doing
actually,
it and then we will learn?
it's very difficult to answer this question for me because now I have not covered any single model, right? So, but yes, so because let's say here we have seen three models, right? Random forest model we have seen, decision tree we have seen, and the linear regression model is we have seen, right? So if if I already know that I'm modeling a no linear relationship, I will never use linear model. Directly, I will use non-linear model. And in fact, if I can afford uh, random forest, I will not use the decision tree. I will directly go with the random forest because I already know random forest performs better than the decision tree. Because in random forest, we are taking multiple decision tree, and since you take the multiple decision tree, then always you will get the better predictions, right? So this type of approach I can use to cut down my uh, some models, right?
Okay, maybe we can discuss the details later, but basically my question still remains that if there are so many models and we don't even know the relationship, right? Because in advance, in a complex data set.
Yes. Then the simple
Not
answer
know.
is we will try all possible combinations, right? Because if we don't know anything about the data, if we don't know anything about the outcomes, then we have to test each and every possible combinations, right?
Outcomes we may know, right? Because there may be a label there.
Yes, outcomes we know, but the relationship we don't know, right?
Correct.
How input is dependent on the output, that relationship we don't know. Then in worst case, the simple answer is uh, we should try each and every possibility, right? But even this answer is not correct because as I said, uh, I already know random forest is performs always better than the decision tree, and if I can afford random forest, then I will not test the decision tree directly. I will check the random, right?
So when we say we can afford, does it mean we can afford the cost of training random
Yes,
for?
the cost of thing, because random forest training random forest is costly. Now for that, I should I should know well in advance that what infrastructure I have, right? Because I will train these models using GPUs. I will train these models using some machine, right? So I should a priori know that this is the computational restrictions that I have, right? So it depends on so many factors, right?
Okay, so maybe we'll cover this later.
Yes.
We'll
So
find out.
we will cover all these aspects when we will discuss these models one by one, right?
All right.
Mhm. So in next step is the fine tune your model. So in fine tuning model, we will decide hyperparameters or the parameters that on which the performance of model depends, right? So you can think there are two types of parameters. There are two types of parameters. First category of parameters are called the model parameters, and we are training model parameters using training data. We are finding optimal values for model parameters using training data. The other type of parameters are called the hyperparameters, on which model performance will depend, right? So for example, the decision tree model. Now the decision tree model depends on the depth of decision tree, right? So because you can create a one height decision tree, you can create a, let's say, two height decision tree, right? Now I can also create a three height decision tree, right? This possibility is also there, right? So now I should proceed with the height one decision tree or height two decision tree or height three decision tree. It's a hyperparameter, right? So that sometimes I have to also decide this part. Should I proceed with the height three decision tree, or how many? What should be the number of leaf node in my model, right? Because here, as you can see, the number of leaf node is 2, right? So here we are having 4 leaf nodes. Here we are having maximum 8 leaf node, right? Okay. So these types of decisions sometimes we also need to we also consider when we are building any machine learning models, and all these decisions will come under the fine tuning part, right? So in fine tuning the model, uh, we will make decisions regarding the hyperparameters, right? Because we can have several possible combinations. We should try to select the best model. And again, here in fine tuning, we will use the validation part, right? Okay. Yes. So let's say if we have multiple models using cross validation, we can select the best model, or if we have the hyperparameters in our model, we can select the best hyperparameter. So for example, in decision tree, in case of decision tree, there are several hyperparameters. So first hyperparameter, you can think like uh, depth of decision tree, right? So depth of decision tree is one hyperparameter. Number of leaf node is again a different hyperparameter. So what you can do, you can have several values of hyperparameters, and you will use cross validation to select the best value of hyperparameter, right? And this process comes under the fine tuning part, right? Yes. Yes. So here we may have hyperparameters in our machine learning model, and the performance of machine learning model depends on these hyperparameters. And hyperparameters we have to decide before the actual training begins, right? So what exactly we will do here in hyperparameter tuning? We will try several uh, values of hyperparameters, and we will pick the hyperparameter value that maximizes validation set performance or that minimizes the validation error, right? So same process we will do here in fine tuning the model, right? We will fix hyperparameter values, and we will choose hyperparameter values that maximizes validation accuracy or minimizes validation error, right? Okay. So here are some examples of hyperparameters. So for example, number of leaves node, depth of tree, the learning rate. Learning rate is a hyperparameters. Number of hidden layers in deep neural network. Number of cluster in K-mean clustering. So don't worry about this part. I will cover all these hyperparameters when I will discuss these models in detail, right? Okay. Now in fine tuning the model, we will use the cross validation, right? Again, the first solution is we can tune hyperparameters manually, right? We can make combinations. So for example, we are having 5 possibilities, so we can check each possibility one by one, or the other options is we can use grid search, right? So you can, so let's say you are building a model using decision tree. You are building a model using decision tree, and in decision trees you are again having 6 possibilities, right? So for example, let's say you are having you are having two two possibilities for number of leaves and 3 possibilities for depth, right? So you are having total 6 possibilities, right? So for example, number of leaf you want to decide, and depth of tree you want to decide. So for depth of tree, assume you are having three possibilities. Let's say 2, let's say 3 or 4. Number of leaves can be, let's say 5 or sorry 4, 5, and let's say yes, 4 and 5, right? So in total, how many combinations we are having? 2 into 3, 6. 6 combinations we are having, right? With 4 leaves, we will try 2 depth decision tree, 3 depth, 4 depth. With 5 leaves, we will try 2 depth decision tree, 3 depth decision tree, and 4 depth decision tree. So therefore, for this variable, we are having 2 values. For this variable, we are having 3 values. So total, we are having 6 possible combinations, right? Now, these 6 possible combinations, we can try manually one by one, right? And what exactly we will do here? We will again use the cross validation. We will use validation accuracy, and we will pick the combination that maximizes validation accuracy, right? Now, this process we can do manually, or we can use grid search that will do this process automatically, right? Yes. So as I said, we are having several combinations of hyperparameters, and we will use validation accuracy. We will use cross validation to decide the optimal value of hyperparameters. And that process either we can do manually, or we can use grid search uh, to decide the optimal value of hyperparameter. Okay, and this process is called grid search because uh, we have created a grid, right? Because let's say here we have option 1, and here let's say we are having option 2. For option 2, we are having 3 possibilities. Option 1, we are having 2 possibilities. So in total, how many possibilities? Are there 6 possibilities are there, right? So since here we are creating a grid type of structure, so therefore this method is called the grid search, right? So in grid search, as you can see, we are covering all possibilities we are covering here, right? Yes. So let's take one example. So here I'm taking random forest regression model, and I'm searching here for hyperparameters, maximum features, number of estimators. So here number of estimators means the number of decision trees that I'm using, right? And maximum feature means the maximum number of features that I can use to build to make the decision tree, right? So, or you can think. So I will cover these hyperparameters in detail in decision trees. So here you can only think like we are having multiple possibilities. So number of estimator is one parameters that we have to decide. Maximum feature is another parameters that we want to decide, right? Now for these parameters we can have 4 values, right? This parameter can be 2, 4, 6, 8, and number of estimator, this parameter can be 3, 10, and 30. So there are total 3 into 4, right? So there are 12 possibilities are there. And again, we are having here bootstrap parameter, number of estimator, and maximum number of feature. So by default, this bootstrap parameter is true, but don't worry about this bootstrap and other parameters. I will cover it in detail when I will discuss decision trees and random forest, right? So you can think in second case we are having 3 parameters. So bootstrap is false. Now in for this parameter number of estimators, we are having 2 possibilities, and for maximum features we are having 3 possibilities. So in total, how many possibilities we have to check? So in first case, 3 possibilities are there for first parameters, and 4 possibilities are there for the second hyperparameter. So in total, 3 into 4, right? 12 possibilities are there, right? Yeah. So in first case, 3 values, 3 possibilities are there for first parameter. 4 possibilities are there for the second hyperparameter maximum features, right? So in first case, there are total 3 into 4 possibilities, right? In the second case, here we are only having 1 possibilities. Here we are having 2 possibilities. Here we are having 3 possibilities. So in total, we are having 1 into 2 into 3, 6 possibilities. So in total, we are having 12 plus 6 possibilities, which is nothing but the 18, right? So in total, we are having 18 possibilities, right? And here we are using cross validation is equal to 5, right? Cross validation is equal to 5. So how many times we will split training data here? 5 times, right? Because cross validation is 5. So we have to test 18 possibilities, and we will decide best possibilities using average of 5 split, because here we have taken cross validation is equal to 5, right? So we will get here 5 error, right? E1, E2, E3, and so on, E5, right? So we will get 5 error, and we will decide using average of 5 error, right? Because here we have taken cross validation is equal to 5. So can you tell me the number of times we will train here our model? How many times we will train here our model? 5 into 18, right? Because we have to check 18 possibilities. We will check 18 possibilities, and in each possibilities we will train model 5 times, because cross validation is 5, right? And then we will select the possibilities that maximizes this average accuracy, that minimizes this average error, or that maximizes this average accuracy, right? Yes. So since here the k is equal to 10, so therefore we are dividing 10 times. But if k is equal to 5, which means we will do this division 5 times, right? So we will get E1, E2, E3 up to E5, and we will take average of 5 errors, right? Yes. So we will take average of 5 errors.
So we are taking average of 5 errors. So how are we getting the using grid search? How are we getting the best hyperparameter?
Yes. So first it will check. We don't know the best combination of parameters, right? So for that we are making grid. So it will take these 18 cases one by one, and for each possibilities, for each combination, it will divide data into 2 parts.
Fivefold, and it will
Fivefold.
train, right?
Yes, it will get the average error, right?
Okay.
Now, after doing this grid search, we will get 18 average errors, right? So we can select the combinations or the possibilities out of 18 possibilities for which we are getting the lowest average error, right? Because what exactly we want? We want lowest error, right? Lowest validation error we want.
So it will be a list of average errors, 18 number list of average errors
Yes,
in
yes.
this case, right? Okay.
But yes, here for this first parameter we are having 3 possibilities. Second we are having 4. So therefore, in first case it will we will have 12 cases, right? 3 into 4. In other case we are having 1 into 2 into 3, 6. So total 18 possibilities we have to change. Right?
Why it is in two different sets actually? So
Yeah,
these are
yes.
all hyperparameters of the same thing, right?
No. But here in the second case, we are having one more hyperparameter, bootstrap. So by default, bootstrap is true. So in first case, bootstrap is true. So what I want, if bootstrap is true, then I want n estimator, this parameters values to be 3, 10, or 30, and maximum features to be 2, 4, 6, and 8, right?
Oh, okay.
Yeah.
Okay.
So this parameter is different in second case, right? So when bootstrap is true, then I want these values. If bootstrap is false, then I want to check these values, right? So total there will be 12 plus 6, 18 possibilities are there. So we have to check these possibilities one by one, and we will pick the possibilities that maximizes our validation set accuracy or that minimizes validation error, right? And in each possibilities, it will do 5-fold cross validation. So in each possibilities, it will train the model 5 times, and it will take average of 5 model, right? So that's why we end up training 5 into model 5 into 18 times, right? Because for each possible combinations, I will train model 5 times, right? So there are total 18 combinations. So I will train model 18 into 5 times here, right? Okay. So, and yes, this grid search CV, I can use, I can import from scikit-learn. So from scikit-learn.model selection, I can import grid search CV. And here in parameter grid, I can define the hyperparameters that I want to explore. So and then I will here mention the model. So random forest regression model. Let's say for random forest regression model, I want to explore these values of hyperparameters. So I will use that random forest model, and then I will pass the parameter grid, right? Because I want to explore these values for these hyperparameters. So therefore, I will write here parameter grid, and then I will mention here I want 5-fold cross validation or 10-fold cross validation. So I will mention here CV is equal to 5 or 10, whatever number I want, and then I will write here the scoring, right? On what basis I want the best model, right? So here I want the best model using error. So that's why here I'm writing negative mean square error, right? Okay, and after doing this grid search, this model, I will get the best model, right? So I will get the best combination of parameters, right? So how can I get the best parameters? Using this best underscore params command. So if I write here, since see here I'm doing grid search using random forest model, and I'm exploring these parameters, these hyperparameters values, right? And I'm using cross validation is equal to 5. I'm using 5-fold cross validation, right? Now, if I want to get the best value of parameters, I will simply write dot best score underscore params, and it will give me the best value of parameters, right? So as you can see here, maximum feature value is 8, number of estimator is 30, which means maximum feature value is 8 and the number of estimator is 30, which means 30,8. 30,8 is the best model, is the model where we are getting lowest cross validation error, right? So 30,8 is the combination where we are getting lowest cross validation error. So this is the best model, right? So grid search, using grid search, we can find the optimal value of hyperparameters, right? So now after doing grid search, I know number of estimators has to be 30 and the maximum number of feature has to be 8. Then I will get the lowest cross validation error, right? And if you want to print the all parameters value, you can also print all parameters by just writing best estimators. So it will output all parameters value for the best model, right? So here, if you only want the parameters that we have defined here, you will write best underscore params. It will return the best value of hyperparameters, right? So since here we are getting number of features 8, number of estimates are 30, which means 38 is the model that is giving us the best cross validation error, right? Because there are total 18 combinations. There are total 18 combinations. Out of 18 combination, 30,8 is the best combination. Is the combination where we are getting the model which results in the lowest cross validation error, right? Okay. And if you want to print the all parameter of best model, then you can write here dot best underscore estimators, and it will output the all parameters of that model. So here, since we are using random forest model, so in this model, these many parameters we are having, so it will print all parameters. So don't worry about these parameters. I will cover these parameters in detail, right? Yes. And if you want to print these results for all combinations, then you can do that also, right? So here, if you use dot best underscore params, it will give you the best value of hyperparameters. But if you want to print all values of the score for all values of hyperparameters, then you will use this code, right? Mean score comma params in a GIP is a function. Then we will use CVRES. So CVRES is a variable that contains the output of grid search, right? So what exactly it will print? Okay, so let me show it on Jupyter Notebook. Yes. Yes. So here first we are making combinations, right? For this parameter we are having 2 combinations. For other parameter we are having 2 combinations. So there will be total 4 combination in case 1. There will be again 4 combinations in case 2, right? Okay. So if you want to print the best model parameter value, you can print that. And in fact, if you want to print the score or the error value, root mean square error for each combinations, you can also print that. So here I'm using for loop mean score comma params, and then I'm using mean test scores and params. So this CVRAS is nothing but the variable that contains the output of grid search, right? So as you can see here, we are having several combinations, 6, 10. So 6, 10 is nothing but our first combination, 6, 10, then 6, 30, then 8, 10, 8, 30, right? Then we have this 6, 10 bootstrap is false, 6, 30 bootstrap is false, 8, 10 bootstrap is false, 8, 30 bootstrap is false, right? So total we will have these many cases, right? Yes, these many cases we will have. So in first combinations where number of features is 6 and number of estimator is 10, this is the error that we are getting. This is the average cross validation error when number of feature is 6 and number of estimator is 10, right? Similarly, 49404 is the root mean square error when bootstrap is false, maximum number of features is 6 and number of estimator is 30, right? So what this cross validation will do, it will select the model that is giving the lowest root mean square error, right? So in this case, as you can see, the lowest root mean square error is, I think, this combination, right? Yes, so this is the combination where we are getting lowest error, right? So in this case, it will select maximum feature 8 and number of estimator 30, right? Yes, maximum feature 8 and number of estimator 30 because, and bootstrap is false because in this case, we are getting lowest cross validation error, right? Any doubt in this code? Okay. Yes. So you can use grid search to decide hyperparameter values, and in fact you can also do this manually, right? Because but if you are doing manually, then you have to test each and every case, right? So and then you will do you will select the best values using uh, cross validation accuracy or cross validation accuracy or validation error, right? Or directly you can use grid search, and grid search will give you the best model, right? But here the problem with the grid search is, if we are having if we are having uh, if we are having so many values for any hyperparameter, then the number of cases will be huge, right? As you can see, even if in this small case we have to train this model 5 into 18 times, right? And assume, let's say, the number of estimators that we want to explore is having, let's say, 10 combinations, and maximum features we are exploring is having 20 combinations. So therefore, in case one only, we will get 200 combinations, 200 possibilities are there, right? Because if number of estimators, let's say, for number of estimator parameters, we want to explore 10 combinations, maximum features we are having, let's say, 20 possibilities, right? So then 10 into 20, 200 possibilities we will explore, right? So then this process is not practically possible, because we have to train model multiple times, right? So then what we will do, we will use randomized search. So in randomized search, what we will do exactly, we will not explore all possibilities, and we will pick these possibilities randomly, right? So for example, what we will do in randomized grid search, we will take one possibilities randomly from one parameter. We will take another possibilities randomly from other parameters, and we will test only for that combinations, right? So in randomized grid search, we will uh, we will uh, we will use random selection, right? In normal grid search, we will explore all possible combinations, right? If 10 possibilities are there for first variable, 20 possibilities are there for the second parameters, then we will explore all possible 20 possible 200 possibilities, right? Because 10 possibilities are there for the first parameter, 20 possibilities are there for the second parameter, so there will be total 200 possibilities. So we will explore 200 possibilities. But in randomized grid search, we will not explore all possibilities, and we will select possibilities. We will do the random selections here, right? Okay. So randomize search cross validation we will use when we have hyperparameter search space is large, right? When we have so many hyperparameters values, then we will use randomized search series. So in randomized search cross validation, we will have one variable called uh, iteration, right? So this iteration defines how many times we will make these combinations, right? So let's take the, the same example. Yes. Assume now we have 100 possibilities for these parameters and 200 possibilities for the second parameter. So then if you do the simple grid search, in that case we have to explore the 100 into 200 possibilities, which is a huge number, right? So for that, what we can do, we can use the randomized grid search. In randomized grid search, we will have one parameter called iteration. So if we define iteration is equal to 100, or let's say iteration is equal to 10, then it will only explore 10 possibilities, right? Iteration parameters, by using iteration parameter, we can control the number of search space, right? So what it will do, so here for the first parameters, how many possibilities we will have? 100. So it will randomly select one possibility out of 100 possibility. So this selection is random here, right? Again, here it will select one value randomly. So we will have one value from this set, one value from this set, and this selection is random, and this is called one iteration, right? So if iteration is equal to 10, which means we will select one value, we will select one value from other variable, and we will repeat this process only 10 times because iteration variable is 10, right? So this way we can cut down our search space from 100 into 200 to only 10, where 10 is the number of iterations that we want to explore, right? Yes. So in each iteration, it will select hyperparameter values random, right? So if let's say if iteration parameter values is 1,000, then it will only explore 1,000 combinations. 1,000 combinations of different values of each hyperparameters, where we are selecting hyperparameters value randomly, right? Yeah. So let's take this example. So here, let's say we want to explore number of estimators and maximum number of features, and here we are using random integer. So this rand int will return a random value from 1 to 200. So there are total 200 possibilities are there for first parameter, and for the second parameter there are total eight possibilities are there, right? This maximum features can be 1, 2, 3, 4, 5, 6, 7, 8. So it will select one value randomly, right? So if you do the normal grid search, the number of possibilities here are 200 into 8, which is huge, right? So here we are not using the grid search. We are using here the randomized search cross validation, right? So here, since we are using number of iteration is equal to 10, so it will only explore 10 cases, right? So what it will do in first case, in first iteration, it will select one value randomly for this parameter. It will select one value randomly for the second parameters, and it will calculate the average error, average cross validation error, right? Now, for the second iteration, again it will select one value randomly for number of estimator. It will select one value for randomly for maximum feature, and it will give us the average cross validation error, right? And it will repeat this process 10 times, right? Yes. And finally we will have total 10 errors, and we will pick the model that is giving us the minimum error, right? So there is nothing much difference in Hello, am I audible?
Yeah, you are.
Yes.
I think, yes, yes. Okay. Yeah, so the only difference between the randomized search and the grid search is in grid search, we will explore all possible combinations, but in the randomized, we will explore the few combinations, right? And we will select these combinations random, right? So for example, here we are only exploring 10 combinations, right? If you do the simple grid search, it will explore 200 into 8 possible combinations, right? Okay. So now can you tell me the benefit of using randomized grid search? When we should use a randomized grid search?
When we have lots of parameters
Yes,
options.
yes. Yes, yes. Because we cannot train a model 1,000 times or 2,000 times, right? So then in that case, we will use randomized search, randomized grid search to narrow down the possible combinations, right? Okay. Yes. So randomized search has two benefits. So first benefit is now we have control over computing budget, right? Because we don't need to train model. So for example, if we are having 10 combination and 20 combination in simple case, we have to train 200 times model, right? So it will require more and more computations power, right? So we can reduce the computational requirements, right? By just lowering down the number of iterations. And the other is and the other benefit is now we can explore few values per hyperparameters, and in fact okay, so let me take a great example. Sometimes what we want, let's say i'm having uh, I'm having hyperparameter, and I want hyperparameter value to be tested, let's say after interval of 5, right? So I want 5 value to be explored, then 10 value to be explored, then 15, then 20, right? So this type of values I want. So what I will do, I can and there also I don't want to explore all possible values. I only want some random values to be tested, right? So then in that case, I will use randomized search, right? Because I don't want to explore all possible combinations, right? So I can reduce my search space using randomized search, right? So it will now check few combinations, and it will not explore all possible combinations, right? Okay, any doubt in randomized search?
Mm.
Okay. Yes, ensemble method. So this ensemble method I will cover in detail when I will cover random forest. But in ensemble method, what we do, we combine, we use multiple models to get the predictions. Okay, so let me give you one simple example so that you can understand ensemble model in a better way. Yes. So let me take this example, right? Suppose you want to predict will it rain tomorrow or not, right? So you want to predict will it rain tomorrow, right? Now, for that, we are having 5 sources, 5 news sources we are having: CNN, BBC, NBC, Doordarshan, Al Jazeera, right? And this is the ground truth. This is the ground truth for 5 days, right? So we want to answer this question, will it rain tomorrow? And for that, we are relying on these 5 sources. And these 5 sources will make predictions for this question, right? Okay. So now the predictions can be correct, predictions can be wrong. So for example, on first day, CNN is saying no. Will it rain tomorrow? CNN is saying no. BBC is saying yes. BBC News is saying no. Doordarshan is saying yes. And the ground truth, actual value is yes, right? So as you can see, if you, and this is the data for the first day, the second row means the data for the second day, data for the third day, right? Now, if you pay attention here, if you check the accuracy of this CNN model, right? One day, first day, it is saying no, ground truth is yes, which means prediction of CNN is wrong for the first day, right? Second day prediction is right, third day prediction is right, fourth day prediction is wrong. So therefore, there are total, we are having total 1, 2, 3, 4, 5, 6 day data we are having, right? So out of 6 predictions, 3 are right and 3 are wrong. So total accuracy for CNN model is 50%, right? Likewise, here also, if you consider, if you see the data, out of 6 possible cases, 2 times this model is correct and 4 times this model is wrong. Oh, sorry, 2 times this model is wrong and 4 times this model is the model prediction is, or this BBC source prediction is, news channel prediction is correct, right? So here the accuracy is 4 divided by 6, right? So here accuracy is 50% because 3 times it is correct out of 6. So 3 divided by 6, 50%. Here, 4 times this source is correct. So therefore, 4 divided by 6 is the accuracy, right? So likewise, if you calculate accuracy for each source, hardly you will get more than 66% correct prediction, right? The maximum correct prediction that you can get using any one particular source is 66%, right? Now what I will do, I will ensemble learning. I will use ensemble learning. I will get I will do the voting, right? So I'm not relying on the single source. Now I'm relying on all sources. 1, 2, 3, 4, 5. All 5 sources I'm relying. And I will do the voting, right? So first day, CNN is saying no, BBC is saying yes, this new channel is saying no, yes, yes. So what is the majority vote here? Out of 5, 3 is saying yes. So I will go with majority and I will say yes, right? So will it rain tomorrow? I will say yes. Ground truth is also yes, right? So my prediction is correct if I am taking ensemble of all 5 sources, right? Other day I will do the same thing. I will go with the majority. Here the majority is no. My prediction is correct, right? Third day also I will go with the majority. Again, third day is my prediction is correct, right? So if you check in all days my predictions are correct, right? Which means if I do the ensemble, if I use the ensemble learning, if I combine prediction from all these sources, now I'm getting 100% accuracy, right? If I rely only on the single source, I'm getting 66% accuracy. But if I use the ensemble learning, I'm getting 100% accuracy. So this is why the random forest will always perform better than the decision tree, because in random forest or in forest decision tree, we are using ensemble learning, right? We are using multiple trees to make the prediction, right? Okay. So in ensemble learning, what we do, we combine multiple models and we improve model performance by combining predictions from multiple models, right? Or again, you can say, let's say we have 10 models, right? And somehow we have selected 3 best models. Now I can use ensemble learning to use all these 3 models to improve my performance, right? So assume initially I am having 10 models, right? And after using model selections, I end up getting 3 best performing models, right? Now I can use these 3 models to improve my performance, right? So what model I'm using? I'm using all 3 models. I'm combining predictions from all 3 models, and that approach is called ensemble learn, right? So it's not like that we will always use one single model. In fact, we can use a combination of model to get the better result, right? So this ensemble learning I will cover in detail, right? Okay. Yes. Then what we can do, we can analyze the best model and their error. So here we have calculated model performance, model error using cross validation, and we have not yet touched the test set. So what we will do, we will now use test data to check model performance over test data. So in this step, we are not doing anything extra. We are only using test data in place of validation data, right? We will use the same model and we will check its performance using test data, right? Yes. Okay. So before that, I want to discuss one more thing. So sometimes depending on what type of machine learning model we are using, we may get an estimate of uh, which feature is important and which feature is not so important, right? So for example, here in decision tree, uh, we will see in decision tree, we will have information gain concept, right? So for some parameters, for some features, information gain is more, for some features, information gain is less, right? So using that information gain, we can estimate whether that parameter is important or not, right? So this part I will cover later, but yes, if you are using decision tree, then in fact uh, we can calculate the importance of features, right? Okay, so if you print the importance of features, feature importance, you can use this command dot feature importance, and it will give you the feature importance, right? So here we are first doing grid search. So grid search dot best estimator, because we want best model. So to select the best model, we will use dot best estimator, and then in that best estimator model, what are the feature importance, what are the importance of each features. So for that we will use feature underscore importance underscore, right? So it will give me the feature importance. So as you can see here, if you print the feature importance, the and we are printing these feature importance in reverse order, in decreasing order. So as you can see here, the most important feature is median income, right? That we already know, right? If we are predicting house price, the most relevant feature is income, median income. So that's why for median income we are having uh, very high value, 0.365, right? Okay. But yes, I will cover this feature importance part in decision tree, right? But here, one point I want to mention here, that for decision tree, we can also print the which also check the which feature is important, which feature is not important, right? Because we are creating decision tree using these features. Using these features, we are creating decision tree. So if decision tree is using this feature, which means this feature is important, right? So if decision tree is not taking any particular feature into consideration, which means that feature is not so important, right? So using that approach, we can also check the important of features, right? So if you check that parameter value, that feature importance parameter value, the highest value you will get for median income feature, which means median income feature is the most important feature, right? Okay, but don't worry, I will cover this feature importance part
But
later,
sir,
right?
if you go back to that one, in
Code.
previous, yeah,
Yes.
here the yeah, here for the Iceland, if you scroll it down, scroll it a bit down. Yeah, the Iceland is showing 5.87. How come it is above 1?
No. 5.87 into 10 raised to power minus 5.
Okay. Sorry, my bad. Yeah, it's the lowest one. Correct.
Lowest one, yes. Because we have arranged these values in descending order, right? In decreasing order we have.
Makes sense.
Yes.
Makes sense. Yeah.
Okay. So now the last step is we will evaluate model performance on test set, right? So here we will not do anything extra. We will only use the test data to check model performance, right? In cross validation, we were checking model performance using validation data. The only difference here is we will use test data to check model performance, right? Okay. Yes. So these steps we have already done, right? So we have tuned the model, we have selected the model, we have selected the best performing model, right? So we have done all these steps, and after doing cross validation, after selecting the best value of hyperparameter, after selecting the best possible models, now we are selecting the final model. Now we are selecting, now we are testing the performance of the best model, right? We have explored all possible values of hyperparameters. We have selected the best value of hyperparameters. We have selected the best model, and now for that best model, for that best hyperparameter values, we are testing the testing performance, test set performance of that model, right? Okay. So get the final model. So since we have done a grid search using all possible combination of hyperparameters and using this dot best estimator, we will get the best model, right? Best model that will give us the lowest cross validation error, lowest validation set error, right? Okay. Now using this final model, we will calculate the performance using test data, right? Okay. So for that we have stratified test set and stratified train set, right? Because we have already divided our data set into two parts, training and test. So this stratified test set contain the test part, right? Because we have divided 20,000 data points into two parts, 20% part and 80% part, which means 16,000 samples are in the training set, and 4,000, roughly 4,000 samples are there in the test set, right? So this stratified test set contain remaining 4,000 samples, right? Yes. Yes. So we have already splitted our data set into two parts, stratified train set and stratified test set, right? So now we are using stratified test set to check the performance of best model, right? So we build our model using training set, and now finally we are using test set to evaluate the performance of our model, right? Yes. So first we are selecting the best model, right? Because we have done a grid search, and after doing this grid search, we know the best model, and the best model here is the model that is giving us the lowest validation error, right? Okay. Now we will use stratified test set, and we will divide test set, because in test data we are having all inputs, we are having all columns, right? So we will separate, we will divide the table into two parts, right? Inputs and output, right? Because in test data we are having all columns, right? So output column is also there, right? So since here we are predicting median house price, house value we are predicting, so therefore we will delete house value, and we also did this step in training, right? In training also we remove this house price column, right? Because this house price value is our output, right? So if you remove this house price value, then you will get the input values and the output values, right? So here output is the house value, right? So this is why we are dropping house value, because house value is the target variable, house value is the output value, right? And the same steps we have already done for the training part also, right? Okay. Now we have to do transformations, because in training data we have done several types of transformations, right? We have done imputing, we have done missing out, we have done imputing values, right? If there is some missing values are there for some features, we will fill those values, right? So we will do the same transformations that we have done for the training data, right? And what type of transformations we are doing for the training data? Imputing, we are imputing missing values, right? Then we are doing feature scalings, right? So same set of transformations we will do. So this is why here I'm doing full pipeline dot transform, so that I can convert, I can apply the transformations that I have done on the test data, on the training data. The same transformation I want to apply over the test data, right? Okay. So it will do all types of pre-processing, right? Because training data also I've done some pre-processing. The same pre-processing I will do for the test data, right? Okay. Now after doing the same pre-processing, I will use test data to make predictions, right? Okay. So here I have the best model. So final underscore model is my best model. And this is the actual output. Median house value is the actual output, and these are the input values. So I will use these input values to predict median house price, right? So x underscore test is the test input data. Y underscore test is the output test data, right? Because just like we have x train and y train, right? So
can we not do the pre-processing in original data set and then divide the data in test?
Yes, you can also do this. Also. Both are equivalent, right? So we have two types of data, trained data and the test data. So X train and X, yes, so train part is there, and then we will have the label part, right? So X train, X test, then Y train, Y test. Sorry. Yes, Y train and Y test, right? So yes, so here X means the input and Y means the output, right? So for training data, I'm having input output pair, for the test data also I will have the input output pair, right? So this X test is nothing but the input in test data. Y underscore test is the output in the test data. X underscore train is the input in the training data. Y underscore train is the output in the training data, right? Because I'm doing supervised learning, so I'm having X comma Y pair, right? Where X is the input and Y is the output label, right? Okay. Yes. So I have prepared X test and Y test, where X test is nothing but the input data for the test set, and Y underscore test is the output label for the test set, right? Yes. Yes. So now I know the best model. I know the best model. I know the test data, input test data, input for the test data and output for the test data, right? Okay. And I will use the same transformations that I have done over the training data, right? So scaling I will do, missing imputing missing values I will do, right? Okay. And then I will use the best model to predict to make predictions using test data, right? So this X test prepared is nothing but the processed test data, right? Processed test data, because I've done transformations here. I've done feature scaling, I've done imputation, right? So after imputing missing values, after doing feature scaling, this X test prepared is nothing but the pre-processed test data, right? Okay. Now I will use pre-processed test data to make the final predictions, right? Now I know I know the actual predictions for the test data. I know the model predictions for the test data. I will use these two to get the mean squared error, right? Because Y test is nothing but the actual predictions, actual values for test data. Final underscore prediction, it is nothing but the predicted value, model predicted value for the test data, right? So I will use mean squared error to get the mean square error, right? And since I want to calculate root mean square error, I will do the root mean square operation, right? Okay. So this is the error that I will get using best model over test data, right? So here I'm not doing anything extra. I'm just I'm using the same steps that we have used for the validation set, right? The only difference is now I'm not using the validation set to evaluate model performance. I'm using the test set to evaluate final model performance, right? So this is the error 47766 is the root mean square error for the best model over test data, right? Okay, so these are the steps that we will follow when we train any machine learning model, right? Okay, so I think I have yes, so 10-15 slides are there, but I think end-to-end machine learning is I have covered. So in next session, I will briefly cover the remaining slides, because in remaining slides, we are I think mainly the repetition is there, right? But yes, I will cover the remaining slides. So I think in next session you will have your quiz, right?
Next week, right?
Yes, next week you will have quiz.
I think the next session will be tomorrow, right?
No, I think next week we will have.
Oh, sorry.
Let me check.
Yeah.
Yes,
Yeah.
yes.
Yeah. So next week, so on Sunday morning, we'll have that quiz, right?
Yes, yes. So I can finish these 10-15 slide in
I think the remaining slides are just summary of what we did, right? Almost.
yes, yes. So if you can give me 5 more minutes, I will finish these slides.
Okay. Yeah. Makes sense.
Okay. Yes. Or maybe if you want, we can take a 5-minute break.
Or we can just go over the summary slides, and if we have any questions, we can do.
Yes,
Because
yes.
because
We can do
5,
it next week only.
yeah.
Mhm. Mhm.
If
Yes,
you have
yes,
any questions, we'll come back on it. It's a
yes.
summary 364. It's a
Mhm.
summary of what we've done.
Yes, yes. Okay. So here we are evaluating a model, but as you can see here, since we are getting 47766 error, so even this model is not so perfect, right? So best model is not so perfect because root mean square error is high, right? But yes, it's not like that. We can only train these three models. In fact, in this course, we will see a variety of courses. So, for example, deep learning models we can use, right? So, in fact, here I have only discussed three models, right? So it's not like that. You can only use three models, right? So, if you use the better model, you will get the better performance, right? So, but yes, still this final model is not so good because again we are having a high root mean square error, right? Yes. Yes. So here the summary is if we have lots of hyperparameters, the performance of model will not be good if if you do over hyperparameter tuning, right? Because what exactly we are doing in hyperparameter tuning, we are we are checking the performance of model again and again using cross validation, right? So which means if you do over hyperparameter tuning, if you tune more number of hyperparameters, then you end up getting the model that is performing good on validation side, right? And if you are not splitting, if you are not using, let's say, 5-fold cross validation, if you are not using, let's say, 10-fold cross validation, and if you are only using one split, then you may get the wrong model, right? So this may be the problem. So this is why we generally do multi-fold cross validation to overcome this problem, and we cut down our search space. So for example, random grid search we will use, right, to cut down the search space, right? Because we don't want model we don't want overfitting, right? Because otherwise if you do lots of hyperparameter tuning, then it may possible that you are getting a model that is only working good for the validation set and not for the test set, right? Because finally what we want, exactly what we want model to be perform good at the test time. For future data we are building this model, right? Okay. So we want a model that performs better at the future time, and this is the reason why we are not using test data in deciding anything, right? So whenever we are having several possibilities, several options we need to try out, we only use the validation data. We never use the test data, right? Because uh, we don't want any decision to be involved in which is involved that is involved on using test data, right? Because test data we will only keep uh, for the uh, because test data we are assuming that the test data is data that we will have at the future time, right? Because we are building this model for the future data. So this is why we will never use test data in deciding any hyperparameter, right? And we will only use the validation data because we want our model to be generalized for the new data, right? Yeah. So now, yeah. So let me give me 2-3 minutes because I think. Uh, Yes. So next phase is present the solution, right? So this step you will use if you are building any product, you are building any machine learning solution for any company, or let's say you are building a model that is predicting something, right? And you want to deploy that model, you want to sell that model, right? So for that you will do this step, right? So you will present the solution. So in this step, what you will do, you will document everything, right? So what have you done, what hyperparameters tuning you have done, and what cases you have explored, right? So these are the model that you have tested out. These are the drawback of that model, right? So all type of documentation you will do here, right? And then you will make presentation, you will present your idea, you will present your model to some industry or to some so for example, let's say you are building a AI based solution for agriculture, right? So for that you will first build the solution, you will follow all these steps, and then you will contact some company that is working on the same field, right? And you, if you want to sell your product to that company, then you will document everything. So for that you will need uh, you will need uh, this step, present the solutions, right? And the last step is launch, monitor, and maintain the system. So here, what we will do, uh, we will uh, we will simply prepare the solution for the production. So you will launch your product, right? You will deploy your model. Now the deployment can be on the local machine, or the deployment can be on the cloud, right? Depending upon how your customers, how your end users are using your system, right? So you for that you will deploy, you will launch your model, and you will deploy your model, right? And then you will monitor the performance of your model, right? Because uh, you have to monitor the system performance after because it may possible that the data that you have used to train your model is different from the data that you are getting real time, right? So you have to ensure that the model is working fine on realistic condition, right? So for that you need to monitor model performance at regular interval, right? And you can set alerts when its performance drops, right? So for example, let's say if your if model is not able to make predictions, or model encountered some problems, then you can set some alert, and then you can either you can do fine tuning your model, you can again retrain your model to fix that problem, right? So all these comes under the monitoring and the maintaining the system part, right? Okay. Now for that, if you explore some problems, that what you can do, you can take help from expert, right? Or you can use crowdsourcing platforms, uh, right? So here also the if your model predictions is not behaving like so for example, model is not working fine, then what you can do, you can take help from expert, or you can trigger some alert messages, so that you can fix that problem, right? So in some cases, what you will do, you will collect new data, and you will again retrain your model to fix that problem. Or what you can do, you can let's say you can use some modifications to your model, so that now you can improve the model performance, right? Yes. And if let's say if a model sometimes we also evaluate models input data quality from time to time, because it may possible that due to some faulty sensors, or due to some fault in the transmissions, the data quality may be degraded, right? So if data is not good, then model performance will be poor, right? Because in machine learning model, data is important, right? If we are not getting the quality data, then the model output will degrade, right? Model performance will degrade. So we need to ensure the quality of data, right? So for example, if any sensor is malfunctioned, then we will not get the correct data. In that case, our model will not perform good, right? Model will make mistakes in that case. So for that, we need to fix any if any sensor problem is there, right? Okay, and especially this monitoring part is important for online learning system, because in online learning system, at a regular interval, we will adapt our model. We will adjust our model so that it can work uh, for the um, for the future data, right? So we have to monitor our system. We have to maintain our system so that model can work for the future data, right? Yes. So maintaining the system is a very simple step. So here we can train model on a regular basis, right? So we can train a model regular basis. We can update model regular basis, right? We can uh, we can use some patches that you can use to update your models, right? And sometimes we also take backup, right? So we can take backup of our data, backup of our model. So for example, if something happens wrong in the future, then what we can do, we can restore model to its previous state, right? So that backup part we can do, or we can restore the previous version of model if something happens wrong in the future, right? Okay. So this maintaining system part, we will mainly take the backup of our data, backup of our system, right? And we will do regular update, right? So in regular updates, what we can do, we can fine tune our model, we can retrain our model if it is required, right? Okay. So the summary part, let me quickly go through this. So yes, so here. Yes. So here, initially we are having. Hello, am I audible?
Yes.
Okay, okay. I think I'm having some problem with my network. Okay. Yes.
Can we cover this remaining slides next week?
No. I
Because
think this is the only this is the last slide. So yes. So for the given data set, what we will do, we will divide data set into two parts: training part and a test part. Now the training part we will use for training our model. Test part we will only use for the final model. We will never touch test part. We only use training part in deciding parameters value. In each and every decision, we will only use training part. We will never touch this test part, right? Test part we will only use one time for the final model, right? Now this training part, we will do several types of pre-processing, right? So depending upon what type of features we are having, and yes, we can also divide this training part into two parts, a smaller training part and validation part. So if you want to decide something, if you want to decide some parameters value, if you want to decide some hyperparameter value, you will use validation part only, right? Okay. Now in the training part, there can be two types of feature: numerical feature or categorical feature. For numerical feature, you can do several types of operations. For example, you can fill out missing values. You can add new attributes. You can create hybrid attribute. You can do feature scaling, right? And for the categorical features, what you can do, you can convert. You can do the one-hot encoding. You can convert categorical features to some one hot encoding vectors, right? And after doing these pre-processing, you will get the final training data, right? Now you will use this pre-processed training data to train your model, and then you will use test data to make prediction, right? Okay, so yes, so if you have any doubt in end-to-end machine learning product, you can we can discuss it in the next session, right? Okay.
Yeah. So, sir, the exam will be on CloudX portal or on this Zoom chat only? How that quiz will be?
Okay, so I will confirm it with Gajendra, and then Gajendra will tell you, right?
Okay, fine. Okay.
Okay, so let me share this slide one more time, so that in case if you don't have, you can download.
Sir, it's there in the it's available on the WhatsApp group, sir.
Okay. Then okay. Thank you very much for joining today's session. And next session, I will cover. I will start new topic, right?
Okay, thank you, sir.
Thanks.
Sure.
Thank you.